Hello everyone, today let's take a look at quantipus number 63, just asking us to prove some basic properties about sets and about conditional probability. So we have these events A and B in a probability space, and the probability of B is greater than 0, so we need to prove the multiplication rule, Bayes' theorem, and the complement rule under conditioning. So let's just get into it down here. So I have some probability space that the events A and B exist in, and in part A, I need to show that the probability of A intersection B is equal to the probability of A given B times the probability of B. All right, this question is really easy. We already know the basic definition of conditional probability, which is right here. So how do we know this? Well, we're given B, so we know that B is true. So now our land of total probability gets restricted down to this green bubble. So now that I know that B happened, what's the probability of A? Well, it's just going to be the A region of this green bubble. But we know that that's just the probability of A intersection B, obviously. And then we just divide that by our new total outcome space, which is just the probability of B, right? So again, basic definition of conditional probability, and all we have to do to get this is just to rearrange it. We multiply each side by the probability of B, and then we wind up right here. So that's all it takes to prove it. Start with the definition of conditional probability and multiply each side by the probability of B. Now in part B, let's just show Bayes' theorem, also pretty simple. So we're trying to show that the probability of B given A is equal to the probability of A given B times the probability of B divided by the probability of A. So we're given A is true, our new total probability space is this green bubble. Now that we're restricted down here, what's the probability of B? Well, it's just going to be the intersection between B and A. So we know that this is just the definition of conditional probability, the intersection of B and A divided by the probability of A. We literally just showed in part A that the probability of A intersection B was equal to the probability of A given B times the probability of B, and then we're just going to take that over the probability of A. So that's how easy it is to prove Bayes' theorem. All we do is we take the basic definition of conditional probability, right? And then we say, okay, this intersection right here, well, it's just equal to the conditional probability of A given B, right? So the red part divided by the orange part, and then we just multiply by the orange part and we get the red part back. So really, if you look at the diagram, this is all we're doing, right? We're saying the probability of B given A, red part divided by green part, well, that's just equal to the probability of A given B, which is red part divided by orange part, times the probability of orange part, which is obviously going to give me the red part back. And then we just divide that by the green part. And obviously red on green is equal to red on green. So really basic equation, but it's very important, you know, it's Bayes' theorem. All right, so now let's go down and look at part C, which might be a little bit trickier. So in part C, we have to show that the probability of A complement given B is equal to 1 minus the probability of A given B. So here's our probability space. So first of all, let's just understand what this equation is saying. What's the probability of A complement given B? Well, it's just going to be if we restrict our sample space down to the B bubble. And then what's the probability of A complement? Well, it's everything not in A complement, but in B. So right here. So now what's the probability of A given B? Well, okay, we're restricting ourselves to the orange bubble again. Now what is the probability of A? Well, it's just everything in A and B at the same time, right? So what is this equation really saying? It's saying that green divided by orange is equal to 1 minus the blue part divided by orange. So if you rearrange, we're just saying that the green part plus the blue part divided by orange is equal to 1. So we're basically saying that the green part plus the blue part is equal to orange, right? And that kind of makes sense just looking at the picture, right? We can partition B into the parts that have A and the parts that don't have A. So now that we kind of know what we're trying to do, let's just solve it using real numbers, right? So we know that the probability of A complement given B is equal to the probability of A complement intersection B divided by the probability of B, right? Basic definition of conditional probability. This is just exactly what we were saying when we took green on orange, right? These are the same here. But you can see we have this blue part in the right-hand side of our equation, so we need to write this in terms of that blue part. In basic set theory, we know that everything in B can be broken up into the things that are in our set A plus the things that are not in our set A. So obviously when we subtract B intersection A from both sides, we get that B intersection A complement is equal to B minus B intersection A. So what does that tell us here? Well, it just tells us that the probability of A complement intersection B is just going to be equal to the probability of B minus the probability of B intersection A. And then if we take that over the probability of B, well, these are going to cancel. We're going to get 1 minus the probability of B intersection A on the probability of B. And what is this saying right here? When we restrict our sample space to B, what is the probability of A occurring? So it's the probability of A given B. So this whole side of the equation is 1 minus the probability of A given B, and we have that equal to the probability of A complement given B, right? That is exactly what we were originally trying to show. So you can see that all these proofs just kind of use the basic conditional probability definition, and then you just kind of rearrange it until you get these new identities like Bayes' theorem, like the multiplication rule, like the complement rule, etc. There's a bunch. And these Venn diagrams make it a lot easier to understand because basic conditional probability is just essentially set theory.